Okay, so we are going to continue with the next properties. So this properties is a differentiation. So if we can refer to this slide, if you are having xt time domain function, so its respective transform is x omega. So if xt is said to be differentiated, so we have dxt over dt. So Fourier transform simply would be x omega multiply with j omega. And if you have n order of differentiation, n order of differentiation, so we have dn of xt over dt. So it's will transform into simply j omega to the power of n multiply with x omega. So this n will be depending on the order of the differentiation, right? And the integration side, the integration properties is if you have xt, then you're going to have x omega. So if xt is said to be integrated, integrated. So it's for transform, it is simply x omega divided by j omega. Yeah. So this is the properties of differentiation. Okay. So let's have a look at the examples. Okay. So we are given these examples here. So the function of ft is given to be 2t plus 4 from negative 2 to 0. Negative 2t plus 4 from 0 to 2 and 0 elsewhere. Okay, so from this given ft, given this function, you have to find number one, what is the first derivative and the second derivative for this ft. So which means that you need to find the first order differentiation and second order differentiation. Okay, number two, you have to find the Fourier transform for first order differentiation and second order differentiation. Okay, so hope you understand the problems stated in this example. So let's have a look at the solution to these examples. Yeah. Okay. So basically, when you sketch the functions properly, the ft, you are supposed to get the ft should be look like this. Okay, which is straight line of 2t plus 4 from negative 2 to 0 and negative 2t plus 4 from 0 to 2. So this is the sketch of this, the ft, yeah? Okay, so let's have a look at the differentiation. So for first order differentiation, we are actually differentiating a straight line. Yeah, so when we differentiate the straight line, we are supposed to get a constant of 2. The same things happen when you differentiate this straight line, you are supposed to get a constant of negative 2. So it should be the first differentiation should be from negative 2 to 0. The second one is from 0 to 2. Okay, yeah. And for the second order differentiation, which is the differentiation of this signal, we are supposed to get an impulse, okay, a positive impulse having amplitude of 2. And then we're going to have a negative impulse at 0 with amplitude of negative 4, and also an impulse positive 2 magnitude at t equals to 2. So we are supposed to get this differentiation results for the second order. Okay, if you still got problem with the differentiation, why we can get this from this first order differentiation, so you can just WhatsApp me for more information, yeah? Okay, so the expression mathematically for both should be equals to, yeah, for this expression, it should be 2 rectangular of t plus 2 plus half. And for the second one here, it should be negative 2 rectangular t over 2 minus half. So I hope you can work out on this expression for the first order differentiation, how we can obtain this, yeah? So I'll have this for you to explore on your own. Okay, whereas for the second order differentiation here, the differentiation value, so this is simply an impulse function. So you are supposed to get positive 2 of impulse t plus 2, okay, which is an impulse which has been shifted 2 units to the left. then we're supposed to get negative 4 of delta t, okay, and you have positive 2 of delta t minus 2. So this is the results. That's the expression for the differentiation. Yeah. Okay, let's have a look at the Fourier transform for both first order differentiation and the second order differentiation. Yeah. Okay, so we are supposed to get for the first order differentiation. Yeah. It is equals to for this one. Yeah, for this one we are supposed to get initially, yeah, for 2 rectangular t over 2, so you are supposed to get forcing of omega. So you can refer to the table how we can obtain forcing omega as a Fourier transform for this function of time domain. So you can refer to the table on your own. So basically, it should be, when we have a time shifting here, where we have 2 rectangular t plus over 2 plus half, so its respective Fourier transform is simply forcing of omega exponential j omega divided by 2. So this is based on the properties of time shifting. Okay, time shifting. Okay, so the same goes to the second expression here, 2 rectangular t over 2 minus half. We are supposed to get forcing of omega exponential negative j omega divided by 2. And as such, when we have these two functions here, where we have 2 rectangular t plus 2 plus half minus 2 rectangular t over 2 minus half, so its Fourier transform is simply forcing omega exponential j omega divided by 2 minus forcing omega exponential negative j omega divided by 2. Okay, so you can also apply this method, yeah, in which we can simplify the Fourier transform for the first order differentiation of xt by simply multiplying the x omega and the j omega, which means that, for instance, yeah, for this first order differentiation, simply we can find the Fourier transform for the dft over dt, yeah, I mean for this expression of rectangulars, by simply multiplying, yeah, j omega with the Fourier transform for these triangular functions. Okay, which means that if we refer to this table, we can use this triangular function to find its Fourier transform. Okay, so we can find the expression of the Fourier transform for this first order differentiation by simply multiplying the j omega with the Fourier transform of this rectangular function, which is supposedly it should be equals to j omega multiplied with a sin squared terms. Yeah, we have a sin squared term there, right? So it should be simply j omega multiplied with this expression. Okay, so that is the properties of the differentiation. So you can try this, yeah, you can try this on your own, yeah. But still, if you got a problem with this, you can just contact me for the information, yeah. So the same goes for the second order differentiation here, yeah, where we have the expression mathematically is given by this. So simply by using a table, we are supposed to get 2 delta function t plus 2. So we're going to get 2 exponential of j omega times 2. And you have 4 delta t, it should be equals to 4. And if you have 2 delta t minus 2, it's supposed to be equals to 2 exponential negative j omega 2. So basically, for this expression, for the second order differentiation, so its respective transform is simply just this, which is 2 exponential j2 omega minus 4 plus 2 exponential negative j2 omega. Okay, so hope it's clear on this. Okay. So the next part will be on convolution. So I'm going to stop now. We're going to proceed with convolution on the part 3 of this lecture. Thank you very much. Yeah. See you then.